The Oregon Trail is a quintessential Apple II game. It seems to be running happily on the SAP 6502 microcode generator and emulator, which is available now. Just follow the GitHub link below, and you may want to check out the first video in the microcode series. This shows you how to download it and compile it. In this series, we have taken the Albert Pulmol-Vino SAP1 design, which was modified and popularized by Ben Eater, and we've bulked it up to run 6502 machine code. We've built the W-bus, the register bank, the controller sequencer, the program counter, and now we're finishing off with the ALU. In the last video, we were able to execute commands up until the time we hit the first RTS or return from subroutine instruction. That failed because we need the arithmetic logic unit to increment and decrement the stack pointer during the JSR and RTS instructions. After the RTS, the next instruction should be at FA66, the instruction immediately after the JSR. Instead, we resume execution at FEFA. This is clearly wrong. We need an ALU to get past this point. You may be wondering why I chose Arnold Schwarzenegger to represent the ALU. Well, the answer is, he's Arnold. That, and because he was involved in one of the best 6502 cameos in a movie.
I'm a friend of Sarah Connor. I was told that she's here. Could I see her, please?
No.
I always thought this scene showed a trace through the code. But if you look at it carefully, this JSR instruction is shown but not executed. So, either it's a listing, or when Skynet watches this playlist in the future, it must have skipped this episode where I try and get JSR and RTS to work. I go over the details of how the ALU on the 6502 works in more detail in these 3 videos. I'll link them below, and if you want more detail, go and have a look there. As I've done with all the other parts of the build, I'm going to start off by looking at what Ben Eater did. His ALU consisted of 2 registers, which fit into an adder, and this fed back onto the W-bus. With some extra logic on the output of the B register, he was also able to perform subtraction. This is Ben Eater's accumulator, and it's quite typical of the way he designs his registers. He uses 2 74LS173 4-bit flip-flops, but they don't have tri-state outputs. This means we can't connect them directly up to the W-bus. Remember our little example of 2 devices trying to talk at the same time?
First, I will be
Chief of the boat.
back by the rules of precedence,
Captain, commanding officer of the USS Alabama.
regulations.
I order you to place the XO under arrest on the charge of
Navy regulations.
I say again, I order you to place the XO under arrest on the charge of mutiny.
Instead, he uses a 74LS245 as an interface buffer. In addition, though, these always active outputs from the flip-flops tend to go to another part of the circuit as well. This entire design is replicated for the B register. Let's draw this another way. We have the W bus on the left. The lower 4 bits of A and B are up the top, while bits 4 through 7 of A and B are down the bottom. We'll come back to this diagram in a moment.
I'll be back.
The outputs from Ben Eater's accumulator and B register are directly connected to the adder subtractor. Let's look at addition first. With long addition, we start at the rightmost column. 8 plus 7 is 15, right 5 carry 1. 1 plus 1 plus 3 is 5 with no carry. 2 plus 8 is 10, write the 0, carry the 1. Carry 1 plus 7 plus 4 is 12, write the 2, carry the 1. The carried 1 plus 0 plus 8 is 9, write 9, no carry. And finally, 4 plus 2 is 6, no carry. When we do this in decimal, we know the rightmost digit down the bottom is our ones column, then tens, hundreds, thousands, tens of thousands, and hundreds of thousands. In binary, however, the columns represent 1s, 2s, 4s, 8s, 16s, and 32s in this case. It turns out we can use almost exactly the same process for adding binary numbers. We operate on one column of the addition at a time. Each column has 3 inputs, the carry in and the 2 numbers above the line, while the same column has 2 outputs, the sum down the bottom and the carry out. From this, we can define the rules for any one column. If the carry in, top and bottom columns are all 0, then the sum's 0, so we write 0 and carry 0. If one and only one of these inputs is 1, then the sum is 1, so we write 1 and carry 0. So far, this is exactly the same as decimal. If 2 of the 3 inputs are 1, then the sum is 2, but now we have a problem. We can't write 2 because it's a binary system. Instead, what we do is write 0 and carry 1. Then we apply the carried 1 in the next column. If all 3 inputs are 1, then the sum is 3. We write 1 and carry 1. Because carry out is applied in the next column, which is a power of 2 up, from this column's perspective, it has a weight of 2. Whereas in decimal, carry out has a value of 10 relative to the current column. Let's apply this to an actual problem. 1 plus 1 is 2, so we write 0 and carry 1. Carry 1 in plus 0 is 1, so we write 1, carry 0. 1 plus 1 is 2, so we write 0, carry 1. Carry in 1 plus 1 is 3, so we write 1 and carry 1. Carry in plus 0 is 1, so we write 1, carry 0. And then finally, 1 plus 0 is 1. If we look at the associated decimal numbers, 45 plus 13 equals 58. We can transform our rules about what to do at any one column into a truth table. From there, we can go directly to a circuit. This is called a full adder. It takes 2 digits and a carry in and produces a sum and a carry out. Part 13 of the Turing 6502 series goes into this in a lot more detail. At this point, you may be wondering how BenEater incorporated this into the SAP1 design. We've already seen that for each bit of the W bus, there's a 1-bit accumulator register and a 1-bit B register. These are fed into a 1-bit full adder, and again we need to have some sort of tri-state buffer to connect it back onto the W bus. This is replicated for all the bits in the W bus. The trick is that the carry out from one bit is connected to the carry in for the next higher order bit. Collectively, these connections form a structure known as the carry chain, and this is actually often what determines the speed of a computer. The problem is, bit 0 needs to be finished before we can figure out bit 1, then bit 1 needs to be finished before we can figure out bit 2. Let's look at another example where we add 6D hexadecimal to 75 hexadecimal. We'll assume that the 6D is in the accumulator and the 75 is in the B register. In BenEater's implementation, for addition, the carry into bit 0 is always 0. So 1 plus 0 is 0 carry 1. 0 plus 1 is 1 carry 0. We keep adding 1 digit at a time with carry transferred between the digits until we hit the most significant digit and we end up with our answer, which is E2. We'll worry about what we do with the last carry out in the next video. If possible, I'd rather avoid having to wire up this circuit for every bit in the W bus. It just so happens that there's a 7400 series logic chip that contains 4 full adders. It contains some smart logic to make carry quicker, but we won't worry about that for the moment. Because each chip only handles 4 bits at a time, we're going to need 2 of them in the SAP1. If we look at BenEater's ALU design and just ignore the status bits for the moment, we can see these 2 adders in the middle of the circuit. The output from our A register connects to both of these adders. During addition, the output of the B register goes through this bank of exclusive OR gates unchanged. So effectively, the B register is presented to the other inputs of the adders. The output of the adder goes through this tri-state buffer and back onto the W bus. Conceptually, we can think of the output of the accumulator and B register as being directly connected to 2 4-bit adders. The output of these go through a 245 tri-state buffer and then back onto the W bus. You might be wondering why BenEater added this large bank of exclusive OR gates. To understand why, we need to look at the 2's complement numbering system of all things. 2's complement is a way of representing negative numbers in binary, and we do it by making the most significant bit a negative number when converting to decimal. The advantage is that we can use a normal adder when dealing with positive and negative numbers. What does this look like in an 8-bit system? Our least significant bit, bit 0, still has a weighting of 1, bit 1 has a weighting of 2, bit 2 has a weighting of 4, and so forth. The big difference is that we give bit 7 a weighting of minus 128. To represent a number like negative 16, we have minus 128, plus 64, plus 32, plus 16. This means the number minus 16 corresponds to hexadecimal F0. How do we turn a positive number into a negative number? Well, first we flip all the bits, so zeros become ones and ones become zeros. Next, we add 1 to the result. 0 is an interesting case. We negate 0 to get FF, then we add 1 to FF to get back to 0. This makes sense. Positive 0 and negative 0 are the same number. 16 is 1 0 in hexadecimal. If we flip all the bits, we get EF. Then we add 1 to get to F0, which is what we showed before. In Ben Eater's SAP1, subtract is done by adding A to the negative value of B. The subtract signal comes directly from the sequencer. When it's low, we want to add A to B, and when it's high, we want to add A to minus B. In the SAP1 design, each bit of the output from the B register is connected up to an exclusive OR gate, while the other input to each of these gates is connected to the SU signal. When SU is 0, the other input to the exclusive OR goes through unchanged. This happens to all of the bits in the B register. On the other hand, when SU equals 1, the other input's inverted. This has the effect of flipping all the bits in B. During subtraction, the output from the A register goes directly to the adders, but each of the bits from the B register is inverted before it goes to the adder. Then, as before, the output goes through a 245 tri-state buffer and onto the W bus. But we still have the problem of adding 1. That's what this pathway is for. The SU signal is connected to the carry input of the adder. This has the effect of adding 1 to the sum. So during subtraction, the exclusive OR gates flip all the bits, and the carry bit does the add 1. So there you have it. A plus minus B. Now this works well for Ben Eater's instruction set, which only really has an add and subtract command. But the 6502 instruction set has add and subtract, as well as AND, OR, exclusive OR, rotate left, and rotate right. It'd be really convenient if there was a 7400 series logic chip that could do all of these. The 74HC181 is almost perfect for the job. It's a 4-bit arithmetic logic unit on a single chip. It can add and subtract, as well as perform the logical functions AND, OR, and exclusive OR. We can do a shift left by adding a number to itself. The main thing that's missing is the shift right. These select signals and the M signal determine what functions carried out by the ALU. This chip does a lot of the work for us, but I don't feel bad using it. It was the ALU chip used in the DataPoint 2200. This design was used to generate the first 8-bit microprocessor, the Intel 8008. This later became the 8080, then the 8085, and 8086. This chip played an important role in microprocessor development. Here's a snippet of the schematic diagram for the DataPoint 2200, and we can see the two 4-bit ALU chips here. How do we upgrade Ben Eater's adder-subtractor design to incorporate a more functional arithmetic logic unit? Well, the first thing I did was change the A and B registers into 74HC574s. This cut 4 chips down to 2. Next, I quite literally swapped out the 283 adders and put in place the 181 ALU chips. The main difference is the addition of these 5 ALU op control lines. These come directly from the control word. 4 of them are connected to the mode select inputs, and the 5th one is this M input, which determines logic versus arithmetic. When ALU op is set to 09 hexadecimal, the whole ALU acts as an adder. When we change ALU op to 1B hexadecimal, the logical AND operation is performed. That's where each bit in the A register is ANDed with each corresponding bit in the B register. When logic op is set to 1E hexadecimal, we perform a logical OR operation. 1/6 gives us the exclusive OR operation. What's really nice is if we set ALU op to be 06 hexadecimal, we get A minus B minus 1. We can use this for subtraction, and we don't need that big bank of exclusive OR gates that Ben Eder had in his design. The only thing we can't do with this ALU is shift right. Instead, what I've done is I've connected this 245 buffer between the B register output and the W bus, where the input B signal is shifted relative to the output W bus connection. B1 goes to W0, B2 goes to W1, and so forth. By controlling the carry input, I can select between a rotate right and a logical shift right. With a couple of these 74HC181 ALUs and a 74245 tri-state buffer, I have enough functionality to implement all of the instructions on the 6502. The most important bit remaining is the status register, which is tightly coupled to the ALU. I'll be going over this in the next video. I want to walk through the build quickly. Obviously, we're looking at the underside of the board. This is the constant register, and this is the ALU op register. These come directly from the control word from our sequencer. I've drawn it as one register here, but actually it's two, mainly because the constant register is 4 bits, sign extended to 8 bits. Next, we have our A and our B register, which are 8 bits each. We incorporated both of these into the register bank over the W bus early in the design. Both of these are connected to a pair of 181 ALU units. These are physically located here and here. The tri-state buffer that connects the output of the ALU back up to the W bus is located in the row of chips above the ALUs. The shift right buffer is located between the ALU output buffer and the constant register, and I put these 3 chips here in a row because they all need to be connected to the W bus. Most of the remaining sockets on the lower part of the board are for decimal adjustment, and I'll have a whole video on that later. Here I've begun wiring in the output of the ALU. This is connected to the 74HC245 tri-state buffer. Wiring up the output of the A and B registers to the ALU units. Now that's getting pretty dense there. I hope I haven't made any mistakes and have to rewire it. This is the W bus extension for the ALU output, shift right buffer, and constant register. I've written a little program in the Arduino Mega so it snoops on the address and data bus into the memory and sends the information to the host PC. Here we see the reset vector fetch at FFFC and FFFD. Next we go to FA62 and fetch the D8 instruction, which is clear D. We fetch the 2084 and FE bytes. This is the JSR instruction. And interestingly, in the middle, we can see it storing the return address to the stack. It actually stores the return address -1. The real 6502 does it this way as well. It means that the RTS instruction has to increment the program counter before starting again. I suspect they did it this way so they didn't have to store the most significant byte of the jump address. Now it performs the LDY FF and then STY at 0 page location 84. Now for the real test, can it execute the return from subroutine command? We see it popping FA65 from the stack, then it increments it by 1 and starts executing at FA66. I'll take this as a win for now. The ALU is incrementing and decrementing the stack pointer appropriately. But to see more of its functionality, we're going to need to have all the status bits connected. That's what I'll go over in the next video. And now we're really getting to the business end. Once status bits are working, I should be able to execute large chunks of code. In fact, it should be able to play a game, It just mightn't do the decimal adjustment properly for the score. Don't forget to like, share and subscribe. And check out the new playlist where I'm going through the microcode one instruction at a time. This will really round out your understanding of how the machine works.